You live in a small town that is quite peculiar by normal standards. It has a very small population where everyone knows everyone. Each building is connected by a street, and you can only access the buildings through these streets. One day, your cat named Goose went missing and haven't returned for days. So, you have no choice but to search every building in town. You take out the town map and try to determine your route. Now, your house is located here at the northernmost part of town and is a dead end, meaning nothing else will be up there, no more roads or path that will lead to some place. Starting from your house, you search for your cat, double checking everything. But Goose, to no luck, hasn't returned. So you figure to search for him first at the left side of town. Not to mention, you have this strong inclination to always go for things on the left. Your first stop was a store, but unfortunately, he wasn't there. So you hit the road again and turned left, heading for the next building. It's your Uncle Hank's house. He invites you in and lets you search throughout the red house, but unfortunately, there's no sight of the cat. It's also a dead end because you don't see any path leading somewhere. So you proceed to the neighboring house, which is the mayor's house. Let's just pretend that you used a secret shortcut to get there. He lets you into his home, but to no luck, Goose was nowhere to be found. So you have no choice but to continue the search on the right side of town. Just like before, we're going to use our secret shortcut. You get to the town hall, but unfortunately, your cat wasn't still there. You take the left road again, as you always do, and search for him in the old lady's house. But still, no sight of that poor cat. You're starting to lose hope. But then you remembered a couple just moved in this newly built house, which can be found if you take a right turn from the town hall. So you go there, knock their doors, and introduce yourself. After telling them what happened, they just smiled at you and let you in their house. With a sigh of relief, you finally found Goose playing with other cats. The couple explains that since they're new in town, they didn't know who the owner was, so they'll have to take care of him temporarily until they find the time to look for his owner since they're still busy settling in. You tell them it's no problem at all, and you're quite grateful since he was in good hands. Plus, he now has his new found friends. So, what does this have to do with a tree?
Oh, by the way, this is a friend of mine, Tree.
I am Groot!
I am Steve Rogers.
Well, not exactly that kind of tree, but I mean a tree in the context of computer science. Let's take this very simple figure of an ordinary tree. It may not be as leafy as you are used to, but it is still a wonderful tree. Now let's try to flip it upside down. In computer science, this is how a tree looks like. You can say it is a computer science tree. Anyway, looking at this tree, notice that it quite looks similar to our town map. That's right, this town map can be a good example of a computer science tree. But what exactly is a computer science tree? Or to be clear, a tree in the context of computer science. A tree is a nonlinear data structure that is made up of nodes that are organized in hierarchy. Now, what do I mean by this? Let's take a look at our town map. Starting from your house, notice that you have access to two roads, which lead to two different sides of town. If you choose to go to the left, you will end up in the store, which will then let you have access to the roads leading to your uncle's house and the mayor's house. Now, going to the right side of town, when you arrive at the town hall, you will then be able to go to the old lady's house and the couple's newly built house. Now, you cannot go directly to one's house without passing by the buildings before it, starting from your house. For example, you went to the town hall looking for the mayor, but was told that he is at his house. Now, you won't be able to go directly to the mayor's house unless you go back and take the streets which will lead you there. In this case, you will have to pass by your house, then the shop, and turn right where the mayor's house is. But for animation purposes, let us pretend that all of that happened in our mystery shortcut. Now, let's discuss each part of a tree using our own town map. The buildings in our map are what we call nodes. These nodes contain data of our program. The first node, which is your house, is what we call the root node. Yes, it's like the root of everything, literally. Imagine it as if it's at the edge of the world, and nothing else will be up there except your house, and you can no longer go further north. In your small town, each building is connected by a street. In a tree, it's what we call an edge, where it functions as a link to the parent node, in this case, your house, to its children, which is the shop and the town hall. Now, these houses, as we mentioned before, are dead ends. There are no more roads or paths that will lead you elsewhere. Now, this is what we call a leaf node, where it's a node with no children. Now, these two neighboring houses are what we call siblings in our tree. Why? It's because they have the same parent node, which is the store. The same goes for these two, with their parent node being the town hall, and yes, the store and the town hall are considered siblings too, because they have the same parent node, which is your house. Now, we also have this concept of descendants and ancestors in a tree. Let's take this newly built house as an example. In order to get there, you will have to start from your house, then the town hall, turn right, then I believe that's it. Now, you can say that the buildings I have mentioned are the ancestors of the newly built house. Basically, ancestors are the buildings you have to pass by in order to get to your destination. As for the descendants, these are the buildings that you will have access to. For example, the descendants of the store are your uncle's house and the mayor's house, while the descendants of the town hall are the old lady's house and the newly built house. We also have these things called depth and height. Let's take a look at a different map where another house is built right here. Depth is the number of edges in a path from the root to a specific node. It's the number of roads you are going to take in order to get to the building you desired. Let's take your uncle's house as an example. From your house, you take this street and this street, and that's it. The depth of your uncle's house is 2. But what about height? Height is the number of edges in a path from the root to the deepest node. See this house that we just built? Well, if you count the number of streets, you are going to end up with 3. And by far, as you can see here, is our deepest node. So, the height of this revised town map is 3. But what about our original map? Can you guess the height of it? If your answer is 2, then I guess you're getting the hang of this. Now, let's talk about the size of a node. Do you still remember the concept of descendants? Last time, we had the store as an example, where its descendants are your uncle's house and the mayor's house. A node's size is the number of its descendants plus itself. So, the size of the shop is your uncle's house, the mayor's house, plus the shop itself, which is a total of 3. Now, there are many different types of trees. Our town map is an example of a binary tree, where you can find at most 2 children nodes for each parent node. Generally speaking, there are different variants of a binary tree. Some of them are strict binary trees, where each node must either have 2 children or no children at all. We also have full binary tree, where each node has exactly 2 children, and all leaf nodes must have the same depth. And lastly, a complete binary tree. Unlike the full binary tree, not all leaf nodes must have the same depth, although it is required to have all leaf nodes to be as far left as possible. We also have what we call generic trees or n-array trees. These type of trees let their nodes to have as many children as they want, may it be 5, 3, or none at all. And oh, I almost forgot to mention binary search trees, which is another special type of a binary tree. It has a few rules for itself. Applying to all parent nodes, all left children must have a less value compared to the corresponding right children. Additionally, every left child must have a less or equal value to its parent node. I know it kind of sounds unfair and truly unjust, but it is what it is. Anyway, here's a quick example. You have a root of 8, and under it, on the left, you have 3, and on the right, you have 10. 3 is obviously less than 10. Now let's take a look at their children as well. 1 on the left is less than 6 on the right. Let's look at how things are going here on the right side. Under 10, we have 14. And since it is greater than 10, we have to put it on the right. And lastly, the parent node 14 has a child of 13, which is less. So we put it on the left. Now what I have mentioned here are just some of the many different types of trees, and I'm pretty sure you're going to learn more of them if you decide to pursue a computer science related career. Now, let's talk about the most exciting part, tree traversals. A tree traversal is the process of visiting all nodes of a tree. That's right, when you went door to all buildings looking for your cat, you were actually performing a tree traversal. There are different types of tree traversals. The ones we are going to discuss one by one are the most common types. The first one is what we call a pre-order traversal. What you did earlier was an example of pre-order traversal. You started from your house, always taking left turns first, you head for the shop, then your uncle's house. Using the mystery shortcut, you then go to the neighboring house, which is the mayor's house. And since it's a dead end and there are no more neighboring buildings, we go to the right side of town. After reaching the town hall, you turn left to visit the old lady's house, and finally, the newly built house. That is the pre-order traversal for you. Next is the in-order traversal, but this time around, we are going to start from your uncle's house, which I'd like to mention located at the leftmost part of town, and again, you have the strong inclination to start things from the left. Now, from there, you go to the store. But seeing another road to the right of it, you decide to visit it first instead of going back home. After visiting the mayor's house, you went home using our mystery shortcut. Now, you're not done with your journey yet because you still haven't explored the right side of town. As I mentioned before, you like to start things from the left, so you take the mystery shortcut to go to the old lady's house. After that, you will visit the town hall, and to complete your journey, the newly built house by the couple who just moved in. Another type is the post-order traversal. You again start from your uncle's house, but this time your next destination is a neighboring house, which is the mayor's house. After visiting the two houses, you go back to the store, but you aren't going home just yet because you haven't explored the right side of town. Similarly, you will start heading for the old lady's house. Then you visit her new neighbors and go back to the town hall. Then head home after a long day. And last but not the least, we have the level order traversal. This is quite different because you will be exploring the town strictly from north to south, west to east. Let's see how that plays out. You start from your house, then you head south. You visit the store and the town hall respectively. After this, you will head further south, starting from the left side, which is west, to the right side, which is east. This will be in the order of your uncle's house, then the mayor's house, the old lady's house, and finally, the newly built house. And I believe that concludes the most common types of tree traversals. In summary, a tree is a nonlinear data structure that is made up of nodes that are organized in hierarchy. Each node is connected by an edge. A root node is the topmost node of the tree. Nodes that have children are what we call parent nodes, and those that have none are what we call leaf nodes. Depth is the number of edges in a path from the root to a specific node, while height is the number of edges in a path from the root to the deepest node. We also learned about the concepts of ancestors and descendants, and the size of a node, which is the number of descendants it has plus the node itself. There are many different types of trees. Some of what we discussed are binary trees in general, and its different variants like strict binary trees, full binary trees, complete binary trees, and binary search tree. Another type that we discuss is the generic trees or n-array trees. And lastly, tree traversal, which is the process of visiting all nodes of a tree. The common types of tree traversals are pre-order, in order, post order, and level order.